G'day everyone. I just did this slide deck and presented it the other day. I decided it might be a good opportunity to put up on my blog simply because there's not a great deal of noob-friendly material about what Anycast is exactly and how it works. So the idea of this video is to give you a rough understanding of exactly what Anycast is, how it works, and give you a full set of configuration that you can go and spin up in your own lab and have a play if you want. So Anycast, the basic concept of it is it routes packets to a single member of a group of potential servers, and they're all identified by the same address. That's pretty important because you've probably been thinking of IP addresses, if you will, as being unique. They don't have to be anymore. So think of an IP address in the Anycast situation that can represent a one-to-one of many association. So a perfect example is Google's DNS service. They run on 8.8.8.8 and 8.8.4.4, I believe. So if you open up a terminal and you type ping 8.8.8.8, no matter where you are, I can guarantee there's going to be a relatively low response time. So it's an example. Funnily enough, my example happens to be DNS. So if I was a relatively large ISP in my home country of Australia, I might decide, I want to give them unique IP addresses if I'm setting up two DNS servers, one in Perth, one in Sydney. Disadvantages of this are that users in Perth have to be able to type this address into their router or computer, and the users in Sydney have to type this address, which could be a little bit confusing for them. The number of others, we'll get to it soon. So an example of setting up these DNS servers with Anycast is that you would be advertising the route for the DNS server out of both Sydney and Australia. So that IP address now being used twice for two different DNS servers. Now, users around the world, or in Australia, that are closer to Perth will be routed to this server to answer its requests. Users in Sydney will be routed to this server to answer its requests. So some advantages is that users get routed to the closest server, decreasing latency, and acts as a geographic load balancer, if you will. So it's very easy to expand out and just add more servers, add to more data centers around the world and start advertising that route in more places. So it can add high levels of availability without having to rely on DNS. That's pretty important because a few ISPs, notably, there have been some discussions on a few mailing lists about an ISP that's not really adhering to the TTL of a domain. So whereas it's been advertised as 20 seconds or whatever the case may be, they're actually, holding it on and then keeping it as a TTL of about a day. So they're not following standards there. And the beauty of using something like this, Anycast, if a data center goes down or you want to start routing traffic somewhere else, generally end users won't really notice it much, and at most it'll be about a minute or a few minutes to be filtered around the world BGP routing tables. One of the biggest advantages is distributed denial of service mitigation. So picture this, if you've got being attacked on an address, that attack now is no longer focused to a single data center, it's now all around the world. We'll get to that in a bit. So one of my favorite CDNs that use is one of my favorite CDNs uses Anycast. They're called Cloudflare, a great company. Try and look them up if you can. They've got a great technical blog. Very, very, very cool company. So they've run through the basics. They've got 23 data centers around the world. And recently, using this Anycast method, they've mitigated an attack of over 65 gigabits a second by spreading the load out by all the servers. Let's think about it. If you're getting attacked by a distributed denial of service attack, some of your traffic might be, coming up from the United States, some of it up in Europe, some of it from Australia. Well, the Australian data center is going to cop the Australian traffic. All around the US, these data centers are going to be, taking the brunt. So not one of their data centers or not some of their customers are going to be impacted. Hopefully it's going to be spread out across all of their data centers. All the data centers are going to be able to cope with that extra load that they're getting, and in their case they've managed to dodge the bullet of this distributed denial of service attack. So other places that have used it, the most notably, I guess you'll find it in the root DNS servers. I won't talk about it too much, but it's well worth the read if you're curious. So I want to quickly introduce you to my lab. This is quickly what I've knocked up to show you the basics of Anycast. We'll talk about a few of the disadvantages too while I'm on this slide. So in my lab, I've advertised the IP address. Let's talk it through. We've got two transit providers with their own unique AS64500 and AS64501, the transit provider 2. Now I've got my data center. So my two data centers belong to the one organization. Let's call it Fred Corp. I don't know, anything you want. So they're sharing the same AS 65000. Now, one thing you'll notice is that these both data centers are advertising the same address, 1.1.1.0 out of both of them, and they're advertising a unique address. So 1.1.2.0 out of data center 1 and 1.1.3.0. And I've got my two ISPs, ISP1 and ISP2. They've got some unique address space there. So let's talk it through. When this user wants to hit up 1.1.1.1, then he'll be routed to the closest. So by this, it has a look at the AS path. Basically, anything that's got the least amount of hops traveling through this AS path will be the closest. So if this guy here is trying to talk to a service on 1.1.1.1, then he's going to be routed to this data center. Likewise, if this guy is trying to talk to a service on 1.1.1.1, then he'll be routed to my data center 2. Now, the beauty of being able to advertise these unique unicast addresses is that if you wanted to talk to a specific server in data center 2, I still can. I just need to be able to talk to its unicast address. Now, one of the interesting things I want to point out is you probably don't source any traffic from this Anycast address. So what I'm trying to say is, if let's say I've got this 1.1.1.1 web server sitting here, and he wants to make a call, a web call or something to, I don't know, something sitting on ISP2, or even if he just sends out a ping, let's say, the data's going to traverse the internet and then get here, but the response is going to end up at a different data center, not where it came from. So it's very important you try not to, source your traffic for requests using these Anycast addresses. They're only really for your end users being able to talk to you. So what I've done here is, in both these data centers, I've got an F5 machine here in this lab, and then I've got a HA proxy CentOS machine, because we're getting lazy by the end of it, sitting here in data center 2. So they're just acting as the VIP addresses, and the servers at the end have this unicast address. So the F5 in this instance is actually going to answer the request for the 1.1.1.0, but it's going to pass that request and establish a new connection to the unicast address for the web server. So if it was going to be doing a lookup or something, then it can do so from its own unicast address. So I'd probably recommend you doing this too. In this lab, I've made the VIP is the Anycast address, but that doesn't belong to a specific server. It's just the load balancer has that VIP and is terminating the traffic on that. So let's get to it and show you a few examples. So here I'm running 2 Windows machines on both my labs. So you can see that the user connected to ISP1, when he looks at that 1.1.1.1 address, he'll get spoken to from the first web server, whereas the user on our ISP2 here will get routed to our second data center. So how does this actually all look here? Well, this is pretty much this lab. It maps very similar. So let's look at one of our transit provider 1. Okay, so if I have a look at this, he's got that 1.1.1.1 Anycast subnet. If we have a look, see, he's got 2 routes for that. One of them's much shorter than the other one. See, him being able to talk to a 65000, the data center, is much shorter than having to hop through the other transit provider before he gets to the end. So that's basically how the shortest stuff works. Now, I want to show you one more quick thing here. If I was to open up my data center 1 here. Now let's see, I remember how I set it up. Yep, so that VIP address is sitting on this interface here when I find my mouse cursor. Okay, I want to show you one pretty cool thing. Okay, so let's leave that constantly being able to ping. Now, if I was to shut down this interface, or withdraw the route, have a look at that. Automatically, we haven't really even lost a single ping packet. The route's been withdrawn, it's been advertised out, and now our data center 2 is now servicing all the requests. So that Anycast address will just start rerouting somewhere else. One thing I did want to add about that is it's best not to use this for extremely long-running TCP sessions. So let's say I've got my Anycast lab working just as it is, and we're downloading, a several terabyte file. So let's say this user here is talking to his data center 2, and he's downloading a file that's several terabytes in length. Now let's say that while this is going on, our ISP2 made a deal with Transit 1, and they established a peer. Now the shortest path might not necessarily be work out through this Transit 2 and then data center 2 provider. So the packet might, mid-transaction, all of a sudden, all the packets might be routed now to data center 1, so it would completely break our session and we'd have to re-establish it and all that kind of muck. So you really got to be careful when considering using Anycast in your environment. Yeah, but that's pretty much it. If you've got any questions, feel free to leave a comment. I'll do the best to answer it. But I hope you've got a better understanding of what Anycast is.